Hello, my name is Tolulope Mohammed, and this is an e-learning video on why a 4-level laser can be more efficient than a 3-level laser. In our modern society, we're all familiar with the use of lasers. Even if you aren't aware of it, the chance that you make use of laser technology on a daily basis is quite high. We use them to listen to music on our CDs, scan product barcodes at supermarkets. Some of us use them to stress up boring parties, while others force and capture our imaginations. However you view them, it is quite clear that laser technology is shaping what we see around us, sometimes even literally. But what is a laser? Well, the clue is in the name. Light amplification by stimulated emission. Waves produced from this emission would generally need to be monochromatic and have both high spatial and temporal coherence. This means that the waves should have profiles looking something like this, as opposed to something like this. But how is this wave used? The nuclei in atoms in an active lasing medium can be modeled as being surrounded by electron orbitals with discrete energies. If a photon with energy equivalent difference in energy between a pair of orbitals is incident upon one of the electrons in the lower orbital, then the electron will gain enough energy to move up to the higher orbital. This is called absorption. Conversely, if the electron was already in an excited state, occupying the second orbital, then an incident photon would make it drop down to the first orbital and stimulate the emission of two photons, both with the energy equivalent to the energy of the initial photon. There is another transition called spontaneous emission, where an electron in an excited state spontaneously emits a photon without any stimulus, but the rate at which this occurs is far less, so for the purposes of this video, we can assume this contribution to be negligible. Spontaneous stimulated emissions are examples of what we call radiative relaxation, but there are other ways an atom or molecule can lose its energy. These are non-radiative vibrational and rotational transitions. These account for the physical and mechanical motion of atoms and molecules. As such, the additional energy levels that the electrons will be able to occupy. But before we get carried away, let's get back to the bigger picture. We've seen that stimulated emission can be produced when energetic photons are incident upon the lasing medium. This emission is then amplified by reflecting it off mirrors to produce constructive interference. So, is this enough to make a laser? This is because absorption and emission are in competition with each other. For us to observe any lasing, the rate at which emissions occur would have to be greater than the rate at which absorption occurs. Therefore, the number of atoms initially in the excited state would have to be greater than those at the rest state. This is called a population. But unfortunately, Boltzmann's statistics tell us that for a normal 2-level system at equilibrium, there is always by far an excess of electrons with lower energy, thereby making absorption the more dominant process. To solve this problem, we need a way of increasing the population of electrons in the excited state relative to those in the lower energy state. To do this, a 3-level. Some atoms have long-lived metastable states between their energy levels. Electrons can occupy these levels. If we manage to pump enough energy to excite electrons into a higher state, instead of instantly falling back down to a lower state, the electrons can undergo fast, non-radiative transitions and fall into one of the metastable levels. If the timing is correct, for a short period, we could have a population inversion between the metastable level and the lower energy level, and once stimulated, emissions of photons will now be the dominant process, and lasing will occur. So, are we there yet? Well, quite. Lasing will be produced, but it is very inefficient. For the 3-level system to work, at least half of the electrons in the medium will have to be excited, meaning a high energy input is required to pump them up to an excited state. Even after this, there will still be a lot of electrons left in the lower level, so competition between absorption and emission will still occur. To solve this, we use a 4-level laser system. The electrons are pumped from the ground level to an orbital 2 energy levels up. If there is a metastable state below it, fast non-radiative losses can now occur, causing a population inversion between the metastable level and the first energy level. There are virtually no electrons in the first energy level, so upon stimulation, emissions with a far greater quantum yield than the 3-level system will be produced. As we don't require as many electrons to be excited initially, less input energy is also required to pump the ground electrons into the second energy level. So, are we finally there yet? Yes, we have a fully functional and efficient laser output. Thanks for watching. Once again, my name is Tolulope Mohammed, and this has been an e-learning video on why a 4-level laser can be more efficient than a 3-level laser.